So last time we have introduced the YouTube manometer. So the principle is quite simple because we have learned that the pressure difference in a fluidic system at two different points. Sorry, let me use the right use a marker. So at those two different points, the pressure difference is basically P2 minus P1 equal to rho G dot H. So dot H is the height difference on the two columns of the two columns. So for the YouTube manometer, you have two inlets here. So you can simply connect one inlet with your pressure source, which you want to measure, and you connect the other inlet with another reference source. So this will form a differential manometer. And also similarly, if you expose P2 at atmosphere, so basically you will have a gauge and pressure sensor, and so you can have gauge pressure sensor and differential pressure sensor. So for this simple format, you can see we need to read two height information or two height values at left and right. So it's not that convenient because you need to take the difference. So that's why people also developed a well type manometer. So this is a well type manometer. So the principle is the same as the regular U-shaped manometer, but instead of having two thin tubes, so on the right hand side it has one thin tube, but the left hand side you have a very large well. So the well has a very large diameter here. So you can imagine if there is a height difference. So let's say I increase my P1. So I increase my P1, and then of course the column here on the right hand side will be increased, the height. And because the D1 here is much larger than D2 here, so that's why D1 is much larger than D2. So you can imagine the height change here comparing to this is almost zero. So that's why you can simply read a single height information on the right hand side tube so that you can have the reading. So it's basically this will be your height difference, so P2 minus P1 will be equal to rho G R. So the R here is just the value here. So you only need one reading. So that's the difference of the well type and the YouTube manometer. And for the well type manometer, we can also have a slightly different version to actually incline the right hand side tube here with a certain angle. So we have an angle here. So actually by doing that, we actually can increase the sensitivity of the manometer. So let me simply derive why this sensitivity can be increased. For the current height difference dot H, so we know that the pressure difference P2 minus P1 will be equal to rho G dot H, and also we know so dot H here is also equal to R divided by sine theta, right? Oh no, sorry. So it's not that. So it's supposed to be. Let me erase it. So it's supposed to be R times sine theta. So that should be R times sine theta. So we can further write. So we can rewrite P2 minus P1 equal to rho G R sine theta, right? So that's the inclined case. So if we don't have the inclined case, so for a regular U-shaped manometer, so we know if R is still the height difference, so this is a regular one, and we know the pressure difference P2 minus P1 is just equal to rho G R, right? Because that's the regular height difference. And the way we read the height on the tube is basically you have those scales, right? So, and also usually you always have the minimum scale. So assuming the minimum scale or the minimum division. So we say that is dot R. So that's the minimum division. So the smallest reading So we want to know, because this is really the limiting factor which determines the resolution of this manometer. So for both inclined and the regular U shape. So we can see what is the smallest pressure difference we can have for this corresponding to this smallest reading. So let's say we use dot P2 minus P1 to represent that. So this is the smallest. So smallest or the resolution, the smallest pressure we can measure. So that will be equal to rho g. So the smallest height here is simply dot r sine theta. So that's for the inclined. And for the regular one, so P2 minus P1 will be equal to rho g. So this becomes the smallest division. So that is for U shape, is regular U shape manometer, right? So you can see those two values are actually the resolutions of both type. So which one is larger? So simply because the different scaling factor here is only sine theta is the difference. So that's why for the inclined manometer, it has a smaller resolution. So that means the resolution of the inclined manometer has been improved. So we can write this down. So inclined manometer. So it has a the resolution has been improved. So keep this in mind. This is maybe something I may test you. So you just need to know why the inclined manometer has a higher resolution comparing to the U-shaped manometer. So also remember, the way we compare it is we know the smallest division on both manometers on the tube is the same. So that is always the smallest division. And then based on this, because we have a different scaling factor here, so that's why the inclined one just allows you to measure a smaller pressure change. So that is the resolution. So you can see the manometer is a very simple pressure sensor device, and also it will not be very accurate because we are relying on visual. And also one more point I want to point out here is because so all those measurement role play. So this is the density of the fluid. So that's why if you have a heavier fluid, and you will be able to have a wider measurement range, because for the same height difference here, and your pressure value will be higher with a higher rho. So that's why I will ask you, let's say, how to increase the measurement range of U-tube manometer. So you can simply say to increase the density of the fluid inside. So the heaviest fluid we know we can find is mercury. So that's why you may need to use mercury if you want to have a wide measurement range. So nowadays manometer is not widely used anymore, but if we go back half a century, so in 1950 or 1940s, so there are many scientific instruments which are using manometer, because at the time other electronic pressure sensors are not readily available. So manometer is actually was actually used for many scientific research. So let's look at one example. In 1940s, actually NASA developed a wind tunnel which is being used to test their supersonic aircrafts. So because at the time there is no electronic pressure sensor available, So actually NASA is using manometer banks to measure the pressure on the surface of the aircraft when they are doing the wind tunnel testing of those aircraft. So because you care about the surface pressure of the aircraft, let's say on the wings here, or on the aircraft body, so that will correlate the fluid dynamics of the aircraft design. So people need to measure pressure on the surface. So what they do, you can see in this photograph, they are connecting those tubes to the surface of the aircraft, and those tubes are finally connected with a few manometer banks. So for this case, each manometer bank has 60 manometers, and you can measure the pressure value at 60 different locations for each bank. So you can see this lady is actually reading the height difference of the manometer, and because you have so many tubes, and human eyes will be not very efficient to record the change or the dynamic change. So what they do is actually they can even use a video. They can take video of the change and then analyze the video so that they can analyze the pressure change. Of course, nowadays we really don't have to use this device because it's pure mechanical. So we always want to measure pressure signal in voltage or current format, which is electronic. So, but still, manometer is a popular pressure sensor device. People, when we talk about or when we introduce pressure sensors, so for that in many textbooks, it is always the first one in the pressure sensor part. And also we have also mentioned that the regular manometer is suitable for measuring differential pressures. So it's differential pressure, or they can also be used to measure gauge pressure, because if you expose one side, either this side or the other side, to the atmosphere, and then you connect your pressure source to another one, so you can measure the gauge pressure. But there is one more type of pressure sensors we know is the absolute pressure sensor. So actually, if you do something, you can also convert U-shape, a tube-based manometer, into a absolute pressure sensor. So what we call it barometer as well. So barometer is just the name of the pressure sensor which are using. Oh, sorry, is the barometer which is used to measure atmosphere pressure. So because in order to measure atmosphere pressure, so one of your port will be exposed to the atmosphere, and of course the other port you need to connect it to vacuum. That means the other port, the pressure is 0. So if you look at the right hand side schematic, and this side, you can regard this as the well, and this well is connected to atmosphere. And the other side is actually a tube which has a sealed chamber, and this sealed chamber there's no gas at all. So this is not easy to make it, but let's say, of course this is just a schematic. So I will show you some practical devices. So let's use this as a example to analyze the principle. So assuming inside is vacuum, is pure vacuum. So it's pure vacuum, and so once you measure the height here, so this height will tell you directly the atmosphere pressure, right? So because here is 0. So because here is basically 0 pressure. But think about this chamber here. So initially this chamber will be 0, but because you have liquid here, you have a liquid interface. So under vacuum, any liquid will be vaporized. So that's why finally inside this chamber there will be a low amount of vaporized from this liquid. So you will never be able to achieve a pure vacuum. So that's why this schematic is useful to introduce the principle, but is not very practical. So the major problem here is how we can control to make, how I have a good control to make a pure vacuum chamber. So here, so let's look at some practical devices. So we call them anaeroid chambers. So anaeroid just means gas-free or air-free. So there is no air. Of course, it's a chamber. So actually, we can make such chambers using some metal structures. And you also may wonder what is the purpose of measuring atmosphere pressure. So I think I have told you some examples before. For instance, we care about weather, and a lot of weather forecasting models. One of the important parameter input is the atmosphere pressure. So when weather change, you have a relative higher atmosphere pressure or lower atmosphere pressure. So atmosphere pressure measurement is useful for weather forecasting, and also it can be used to measure altitude. So this is actually a altimeter. So where we measure the atmosphere pressure, so we correlate the atmosphere pressure with altitude, because we know once you have a higher altitude, let's for instance in the plane, and the pressure will drop significantly. So there is a kind of fixed relationship. So we can measure we can measure altitude by quantifying the atmosphere pressure. That's why barometer, a lot of examples, so barometer is used for predicting or measuring altitude. So this slide shows you two designs of barometers. So they share the same structure, which is the anaeroid chamber. So if you look at the left-hand side example, you have an anaeroid chamber here. So it's a metal-made chamber. The chamber is actually finally sealed in vacuum, in high vacuum. So you can see this is a chamber. This chamber is compressible along this direction. It was sealed in a vacuum environment. And you can imagine once this atmosphere pressure is applying to this anaeroid chamber, and the lever here will finally move the pointer to different location on the scale, right? So that will tell you atmosphere pressure is higher or lower, and we can quantify that to have a calibration. So that's a simple example. Another example here is a practical device of altimeter, so which is the altitude meter. So you can see inside we have this anaeroid chamber here. It is also sealed in vacuum, so you can have nearly zero pressure inside. So once you have the atmosphere pressure is applied here, so you can see it will be finally compressed, and you have a lever connected to the center of the anaeroid here. So this is a connection, and then once the anaeroid chamber is compressed, so it will drive, this lever will drive a cable and finally rotate the central axis and move the pointer. So that's how it works. And this is a photo of this device. So this is schematic. This is a photo. It is actually a practical altimeter. So you can see the anaeroid chamber is inside here, and this indicator indicates the height or the altitude difference. So this is still the device all the aircrafts are using to measure altitude, because this device is nearly 100% reliable. So it's more reliable than electronic altimeters. So aircraft you always want to have a double reliability design. So usually this will be the final one to measure the altitude. Okay, so far we have seen the tube-based manometer, and also we have seen the anaeroid chambers, which is being used for making barometers or altitude meters. So let's look at another type of pressure sensor. So if you look at this photo here, so this is a regular pressure gauge. So you can find it almost any gas cylinders, compressed gas cylinders. So it's a simple mechanical device. There's no electrical components, and it's quite reliable. Of course, the resolution or the sensitivity, sorry, the resolution or the accuracy of this guy is not very high. So we're talking about plus minus 2 to 5% of your reading or your full scale. But it's good enough to indicate the internal pressure of a compressed air tank. And let's look at the schematic of this. So this gauge, we call them burden gauge. So if you look at the schematic of this device, so you have a kind of tube in such a circular shape. So this is a tube. The whole tube is enclosed. So let me remove this line. So the whole tube is enclosed. That's the wall, and this is your inlet here. So you supply a pressure signal inside, and if you look at the cross-section view of the shape of the tube, it's kind of a compressed circular shape. Here you can see, and this is the direction here. So you can imagine once you increase the pressure, once you apply a pressure, so this tube will tend to be deformed along this way, right? So this dotted contour indicates the position of the endpoint here after the deformation. And also the endpoint is connected with a lever mechanism and a gear pair. Finally, it will drive the indicator or the pointer to move along the scale direction. So you can see you move this indicator, and this is the principle of the burden gauge. So this photo shows you the internal structure here, and this is the burden tube. You can see this is the burden tube. This is the lever connection, and finally it's connected to the pointer. So again, this device has a relatively low accuracy, but is simple and reliable, and we usually use it on the compressed air gas or some pressure measurement devices where the accuracy is not required to be very high. So the next pressure sensor we will introduce is called dead weight tester. So this is the last mechanical pressure sensor we will introduce, and it's actually a unique one because the dead weight tester is usually used for calibration of other type of pressure sensors. So it is for calibration. So the reason why this dead weight tester can be used for calibration, of course, is because it has a higher sensitivity, has a higher accuracy. So we can control the accuracy to be a high level. So let's look at the structure of this dead weight tester. So you can see this is a schematic of the dead weight tester. So it has an internal chamber here, and usually this chamber is filled with liquid or gas. So sometimes we use oil, sometimes we use other fluids or gas. So you have a single inlet here, and this inlet is used to connect with the device you want to calibrate, or with this is the pressure sensor you want to calibrate here. And this is actually a burden gauge connected to the inlet. And once we connect the burden gauge to the inlet, and we can apply a known pressure to here, so we can do a calibration, right? So how we can adjust the known pressure accurately is by this way. So you can see you have a airtight sealed cylinder here, and it can move up and down. So this is the pistol. The pistol can move up and down, and you on the top of the pistol you can add a weight with a known mass or weight. So of course if you add more weight here, so if you increase the weight, and the weight divided by the cross-section area here, so if we say the area here is A, so W over A becomes the pressure here. So that's the pressure at this interface, right? So let's separate it. So you can see the cross-section area is, if the pistol is usually a circular shape, so we can use lasing machine to machine the pistol diameter to be very accurate, and also we can accurately calibrate or measure the weight we apply. So both parameters, we can control them very accurately so that we can control the pressure at this interface very accurately. So if we can adjust the interface here to be at the same level at the interface here, so for oil or any liquid, we know if I give a subscript here, so I name this is to be P1 and this to be P2. So if I adjust the two height at the same level, so P1 and P2 will be the same, right? So let me write it here. So P1 will be equal to P2 if the piston area, which is the bottom area, sorry, it's not piston area, it's a piston bottom surface. So if this surface is at the same level with the inlet. So the question is how we can adjust it. So that's we design a hand wheel here. So you can turn this hand wheel so that you can move the position of the thread. So if you move the thread a little bit inward, we can actually lift up the whole piston and the weight, right? So if you lift it up and finally you can adjust it to be the same height. So that is the principle of dead weight. So how we adjust the two height of the two interfaces is we use the hand wheel. Okay, so let me summarize the testing point of this dead weight tester is you need to know how to calculate the pressure P1 at the bottom interface here. So P1 is just equal to W divided by A. So the W is the weight here, and if the piston has also a weight, let's say it's W0, so we also need to add the piston weight. Sorry, the piston weight. Sorry, I keep saying piston. So it should be piston. So this is the piston weight. This is the real weight we apply. So you need to sum up the two weight and then use it to divide the cross-section area. So there could be some calculation questions. We ask you to design a dead weight tester. For instance, I ask you the diameter, how to determine the diameter based on the desired measurement range. So that's the first testing point about determining the pressure. And the second testing point is you need to understand the two surface here, it has to be at the same level. So at the same height. So let me use blue pen. So at the same height, I mean the two bottom interface, and also how we adjust the two interface here to be at the same height. So we adjust by the hand wheel. And the fourth point here is why it is suitable for calibration. Why it's suitable for calibration. So the reason is just that we can control both parameters, the weight parameter here and the cross-section area parameter here very accurately, because you can do lathe machining to determine the piston diameter very well, and also we can accurately measure the applied weight. So pulse parameters can be determined very accurately. So that's why finally the applied pressure here will be determined accurately. So that's the major reason the dead weight tester can be used for pressure sensor calibration.